All right, y'all. So this is the energetics part two, HL and SL test. The first part of the test is SL, and then the back half is HL. So stick around for what you need. So what is the number one? What is the value for enthalpy of formation of methane from the given enthalpies of combustion? Now, because we have these enthalpies right here, we're just going to be summing these. This is that Hess's law such stuff. So one thing I noticed is carbon on the left, carbon on the left. Don't have to change that. Hydrogen on the left, hydrogen on the left. Now, there are two, so I'm going to multiply this whole formula by 2. Therefore, multiplying this value by 2, providing me with negative 572 kilojoules per mole. I'm going to stop writing kilojoules per mole because it's faster. I have methane on the right, but I have methane on the left, so I need to reverse this formula. So I'm going to take the whole thing and multiply it by a negative 1. Again, going to do the same thing over here, and I get positive 891. Now, when I add up all the math, I have negative 394. So all of these start with that, which means they're good. Uh, Minus 572, or 2 times 286. So we have that here, but not on A, not on C, so it's got to be B or D at this point. And then finally, plus 891 right there, plus 891. So our correct answer is D. Let's go ahead and actually just highlight that in green. All right. So which combination of delta H1, delta H2, and delta H3 would give the enthalpy of this reaction? Again, it's the same thing as before. I'm going to try and identify what products and reactants are where. So I notice that I have CO2 in the reactants and CO2 in the reactants. Perfect. I do not have to change delta H1. Delta H1 is fine. I notice that I have sulfur and oxygen and SO2. Sulfur is not really around, but oxygen is on the correct side. SO2 is on the correct side. However, we have a coefficient of 2, so I'm going to multiply this one by 2. So I have 2 delta H2. Lastly, I notice that I have carbon disulfide on the product side, but I need carbon disulfide on the reactant side. So I need to multiply that by a negative 1. So I should have negative delta H3. So whatever I do, I should have a positive delta H1, 2 times delta H2, and a negative delta H3. So they all start with positive delta H1. Only C and D have 2 times delta H2, and D over here has negative delta H3. My correct answer, once again, is D. All right, which statement is correct about identical pieces of magnesium added to two solutions, X and Y, containing hydrochloric acid at the same temperature? So this is where we want to visualize one of these graphs where the temperature goes up and then falls. And our max temperature for either graph is dependent on the heat loss, because if we can make the reaction happen faster, we can make the maximum temperature higher. And so basically what it's asking is which of these is likely to make the reaction happen faster? A lower concentration or a higher concentration? And to me, the higher concentration is going to incur more uh, a faster reaction. There's a lot more particles in close proximity, so solution X will reach the higher temperature faster. Which combustion reaction releases the least energy per mole of C3H8? And we have approximate bond enthalpies. So really what we want to do is identify the differences here. You'll notice some of these reactions produce, some of these reactions produce CO2, 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 and some of them produce carbon monoxide, CO, CO, CO. And that's kind of the main difference here. We always get the same amount of water, and we're always using some oxygen. Now, the big difference comes within carbon monoxide and carbon dioxide. Carbon monoxide, which I've circled in green, has this triple bond O, which has 1,000 kilojoules per mole. So that's a lot. While carbon dioxide only has C double bond O, which is 800. So you tend to think that anything with carbon dioxide would produce less energy than carbon dioxide because 800 is less than 1,000. Kind of common sense. But here's where the catch comes in. carbon dioxide has not one, but two of these double bond O's. So the products that create carbon dioxide actually have 2 times 800, at which case that's 1600. So that's going to have more energy. And because it has more energy, the product with the least energy will be the one without carbon dioxide, which is going to be D once more. So we're always looking at the changes in energy in these products. And so we have to really just kind of analyze the patterns and trends that they give us. All right. Which reaction represents standard enthalpy of formation of lithium oxide? Well, standard enthalpy of formation means that we are making 1 mole of Li2O, so automatically cannot be A and cannot be C or D. Oh, okay. Answer has to be B. Standard refers to 1 mole. We have to remember that. Okay. Which statement describes an endothermic reaction? Endothermic. So endothermic is where we have a positive delta H. That's generally referred to as endothermic. Now, looking at A, bonds broken are stronger than bond formed. So we're looking at the bond enthalpy because the bond enthalpy equation, delta H, is equal to the sum of the delta H of, or sorry, sum of bonds. Yeah, it's delta H of bonds broken minus some delta H bonds formed. Okay, so using this equation, if the bonds broken are stronger than the bonds formed, then that means they have higher energy. Therefore, if they have higher energy, this will create a positive value. So it's got to be A. Basically, if the bonds broken are stronger, so like if the bonds broken are like maybe 10 and the bonds formed are 8, well, 10 minus 8 is a positive 2. That's a positive value, positive delta H, endothermic. I don't need to read the rest. All right. If the overall enthalpy of reaction is exothermic, the bonds broken have more energy or the bonds formed have more energy. This is the exact opposite of number 6. So if you got number 6 right, chances are you got number 7 right as well. Bonds formed. So endothermic bonds broken have more energy, exothermic bonds formed have more energy. What is the change in enthalpy in joules when 5 grams of water is heated from 10 to 18 degrees Celsius? And they give us a specific heat in kilojoules, but it's also per kilogram. So that's the little tricky part here, because if you take 4.184 or 4.18 kilojoules per kilogram to convert that to Kelvin, sorry, to convert that, we would need two conversions. 1 kilojoule is 1,000 joules. So that would imply we're using these 10 to the thirds or 10 to the minus thirds. But we also have 1 kilogram is equal to 1,000 grams. So these just cancel out. And 4.184 is still 4.18 joules per gram Kelvin. And because of that, when you use Q equals C delta T, it's 5 times 4.18 times 18 minus 10, which is equal to 8. So it's A. Whoops. So yeah, we don't have to actually make any changes. All right, which combination gives you the enthalpy change for the hydrogenation of ethene to ethane, delta H3? So we're looking for this one. So this isn't as bad as it appears. Basically, we're looking how to go from this thing all the way to this thing. But we cannot just say delta H3. No, no, no. So let's go through it. Well, we're going backwards on delta H2, so negative delta H2. Then we're going forwards on delta H1 plus delta H1. Then we're going backwards on delta H4, so negative delta H4. So we have to look for the combination that has negative delta H2, negative delta H4, and positive delta H1. So we can see that it is going to be A. So really, we're just following the chart here. We're not actually doing much else about it. All right. Number 10 is a question I removed from the test. Don't worry about it, because for the record, I thought we were calculating this, didn't read the question fully when I put it in. Calculating percent uncertainty. I'll give you a quick little approximate how to do it. We just add uncertainties. So here, the uncertainty is 0.2 divided by 20.2, which is about 1%. Here, 1 divided by 10 is about 10%. The total uncertainty is 11%. It's really not a hard question, but there it is. All right, number 11. Which equation represents the NH bond enthalpies in NH3? So what we're trying to identify in NH3, which has 1, 2, 3 of these, is just 1. So we're looking for 1 out of 3, or 1/3 NH3. There's only one thing that actually references 1/3 NH3. That's B. There's our answer. When equal masses of X and Y absorb the same amount of energy, their temperatures rise by 5 degrees and 10 degrees respectively. Um, so what this is saying is that for the same energy, so let's say same energy, we can't use X. Let's do same energy Q. Q is equal to an equal mass, M1, specific heat X, and 5 degrees times 5. Same Q, Q1 is equal to M1, specific heat Y, and 10. If we equate these, therefore M1, because these are the same, we can just equate them. M1 CX 5 is equal to M2 CX 10, or sorry, and it's not M2, it's still M1 because they have equal masses. We cancel out the masses, we divide by 5 on both sides, and we get the specific heat of X is equal to 2 times the specific heat of Y. And therefore, A, the specific heat capacity of X is twice that of Y. What is the enthalpy change of reaction for the following equation? So again, we're just going to try and identify where each part is. I notice that CH4 is on the reactants. So here, CH4 on the reactants, no change. We're cool. I notice C2H6 is on the product. C2H6 is on the products, but it's on the reactant. So I need to multiply this whole thing by a -1 to flip it. So we have X stays the same, negative Y, and let's see. H2, it's in the correct place. So a Z, positive Z. So our answer has to have X minus Y plus Z. So that is, unfortunately for me, on the next page, D. All right, consider the following equations. What is the standard enthalpy change in kilojoules for the reaction below? So I notice, first off, that aluminum on the reactant side and aluminum on the reactant side. The only difference, though, is we have 2 coefficient and a 4. So I'm going to take this whole thing and multiply it by 2. Got it. Next one. I notice manganese on the products, but manganese on the reactants. And I notice 3 and 1. So I need to multiply this whole thing by -3 so that I can flip it and multiply by 3. So we have 2 times -1670 plus 3, -3 times -520. This negative and negative will cancel out to become a positive. So I end up with 2 times -1670 and 3 times 520 to get D as my answer again. All right. Methane undergoes combustion, incomplete combustion. What is the enthalpy change in kilojoules using the bond enthalpy data given below? So we have to take our individual molecules. Methane is CH4, H, 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 H. Oxygen is O double bond O. Now we have times 2 of these and times 3 of these. We produce C triple bond O, but we have times 2 of these, and H2O times 4 of those. So what we need is 2. So, and sorry, once again, we're using bond enthalpy. So bond broken minus bond formed. So bonds broken minus bonds formed. So we have 4 CH bonds, CH bonds, but we have times 2 of them. So we have 8 times CH plus 3 O double bond O, 3 times O double bond O. That we are subtracting from, 2 C triple bond O plus, again, we have 2 OH bonds, but times 4, 8 O bond H. So what we're looking for is something that follows this formula. And when I plug these values in, I see 8 C bond H right here, 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 and here. So I know my answer is C. I'm just taking the values from the chart. All right. 16, consider the following reactions. We have iron oxide plus carbon monoxide and iron plus carbon dioxide, and we are producing this equation down below. I see iron oxide on the reactant side. That's good. No changes needed. So we'll keep our -3. Then I see iron on the reactants and iron on the product. So I'm going to need to flip it. In addition, I need to multiply by 2. So times a -2. So I'll have -22. -3 plus -22 is -25 for a final answer of A. When you do these, you don't have to try and match every single thing. You just have to match a couple key terms and the equations will fall into place naturally. And that's kind of one of the tricks that people don't often realize with it. So moving on with this one, which is correct when barium hydroxide reacts with ammonium chloride. First thing I notice, delta H is positive, which means the temperature will decrease. That's because it is endothermic, meaning it's taking energy from the environment into itself. So the overall temperature will decrease. So it has to be B or C. Furthermore, if it is endothermic, when I look at an endothermic graph, it looks like this. So I know that the products have a higher enthalpy, not lower enthalpy. Therefore, my answer must in fact be C. Products have higher enthalpy. All right, moving on to 18. Now with 18, we're just kind of doing the same thing over and over. We're looking at bond enthalpies. So we're doing bonds broken minus bonds formed. We have the N triple bond N broken plus 3 H bond H broken minus 2 times 3 times N single bond H. So when I do this whole thing, I find N triple bond N Y plus 3 H bond H X minus 2 times 3 is 6 times Z. Y plus 3X minus Z, or 6Z, C. All right. Moving on. Number 19, calculate the enthalpy change in kilojoules per mole for the reaction above. Use bond enthalpy values in the table below. No table, you need to use it from your book, your data booklet. So let's go ahead and count all these out. So again, first I'll start off with bonds broken minus bonds formed. All right, so our bonds broken. We have 4 times carbon single bond hydrogen plus carbon double bond carbon plus bromine single bond bromine. Those are all the bonds broken. Our bonds form that we're subtracting from is 4 times carbon single bond hydrogen. 1, 2, 3, 4. Plus carbon single bond carbon plus 2, sorry, plus 2 times carbon single bond bromine. Now we can simplify it because the carbon times hydrogen, 4 of each on each side, will cancel out with each other. And we just end up with a much nicer value of carbon double bond carbon, which that one becomes 614, plus bromine single bond bromine is going to have a value of 193. Subtract that from carbon single bond carbon, it has a value of 346 minus, or sorry, not minus, plus 2 times carbon bond bromine, which is 219. So I'm going to go ahead and plug this into my calculator, and I get a final answer of 23 kilojoules per mole. All right. Number 20. Write the equation for the complete combustion of ethanol. Ethanol, or ethyl alcohol, is C2H6O. Complete combustion means we react with oxygen to produce CO2 plus H2O. I'm going to balance this out. I realize I need 2 carbons. I need 3 waters, or 6 hydrogens, so I need 3 waters. And that's going to give me a total of 3 plus 4, 7 total oxygens. 1 oxygen's accounted here, so I need 6 more, and we are balanced. Now, here's the deal. Now that we're in our second year, we're going to start using state symbols. Ethanol is a liquid. It's alcohol. When you look at alcohol at room temperature, it's a liquid. Oxygen's a gas. Carbon dioxide is a gas. Combustion produces not liquid, but gaseous water vapor. So let's start throwing those in. Determine the enthalpy change for combustion of ethanol in kilojoules per mole using section 11. So again, we're going to be using our bond enthalpies here, which means you have to derive the structure for ethanol. Now, deriving the structure for ethanol might seem complex at first, but there's only one possible structure you can actually make to include everything. That would be 1 carbon with 3 hydrogens, another carbon with 2 hydrogens, and a final bond to an oxygen, which is bound to a hydrogen. That is the only possible way you could do this, satisfying every atom while also allowing for every atom to be used. We're going to bond that to 3 oxygen double bond oxygen. When we react that, we get 2, and you know what? Actually, this time I'm going to make it a little easier. We have 3 oxygen double bond oxygen. Just going to draw them out. We have 2 carbon dioxides, C double one O double one O, C double one O double one O, plus 3 water, H O H H O H H O H. So we need to take all our bonds and compare them. When I look at this, I notice that I have 5 times our C single bond H bonds. I notice I have 1 C single bond C, and I have 1 O single bond H. I also have 1 C single bond O. There's all my bonds there. I have 3 O double bond O. I have 4 C double bond O. And I have 6 O single bond H. Before I do, once again, bond broken minus bond form, I do notice that I have O bond H and O bond H, so I'm actually going to cancel this out a little bit. We're out of these, and this goes from a 6 to a 5. All right. So I'm going to go ahead and do broken minus formed. That's going to get me a pretty large set of values. That's going to be 5 times 414 plus 346 plus 346 plus 498. Am I missing something here? Oh, yes, I am. Sorry, plus 358. These are just the ethanol plus 3 times 498. That is my oxygen. And I'm going to subtract that all from 4 times 8. Whoops. I'm going to keep things together. 4 times 804. That's my carbon dioxide. Plus 5 times, oops, OH is 463. So that covers that. So these are all my bonds broken minus all my bonds formed, and I get a delta H standard. This is standard because we only have 1 mole of combustion of negative 1,263 kilojoules per mole. And we did it. Ammonium nitrate, NH4NO3, is used as a high nitrogen fertilizer. Calculate the percentage by mass of nitrogen in ammonium nitrate. All right, well, I have two nitrogens here. So nitrogen weighs 12.01. So 2 of them is 24.02. Or sorry, whoa. I made some mistakes here. Carbon is 12.01. Nitrogen is 14.01. So 2 is 28.02. Whoops, almost started bad. I know that the full mass of ammonium, by calculating it out, 2 times N plus 4 times H plus 3 times O. That's going to be a total of 80.08 grams per mole. These are molar masses. This is also grams per mole. So 28.02 divided by 80.08 is equal to a grand total. Oh, you know what? I made a mistake here. Another one. It's not 80.08. It's 80.06. 06. That's a grand total of 35.00%. When you multiply by 100. You'll notice I actually have 4 significant figures because I'm adding these values that all go up to the hundredths place. Therefore, my answer should be in the hundredths place. And then when I divide by 2 things with 4 significant figures, I end with 4 significant figures, 35.00%. Deduce the Lewis electron dot structure for the nitrate ion. Well, we can do this a couple ways, but I'm going to go ahead and just draw nitrogen with its 5 valence electrons. I will connect an oxygen and I will double bond it to make oxygen happy. Then I know that we have an NO3 minus. We've got that free little electron. I'll add it here. Now nitrogen has 2 lone pairs for which oxygen can just go ahead and coordinate covalent bond onto. This whole thing has a negative charge, and I will in fact redraw it using proper angles as well as proper diagram notation. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 4, 5, 6, 7, 8. Perfect. Yes, everything fulfills the octet rule. All the oxygens are happy, and nitrogen has a full octet, and we have a negative charge. Moving on. Cold packs containing aluminum nitrate and water are separated by membrane. The mass of the contents of the cold pack is 25.32 grams. Its initial temperature is 25.2 degrees Celsius. Once the contents are mixed, the temperature drops to 0.08. Calculate the energy in joules absorbed by the dissolution of ammonium nitrate in water within the cold pack. Assume specific heat capacity is 4.18 joules per gram Kelvin, using section 1 of the data booklet. Basically, we're using Q equals mc delta T. Our mass is given to us as 25.32. We can keep grams because our C is in grams, so 4.18. Our temperature change is 0.08 to 25.2 to 0.08, which if we do that out, 25.2 minus 0.8 is equal to 24.4. Now, the solution is negative. It changes in a negative direction. The temperature goes down. However, because the solution goes down, what they mentioned is this is being absorbed by the nitrate. That heat is absorbed by the nitrate. Therefore, we are looking for a positive value, and we will use the positive difference, 24.4. So when we calculate this out, we get a total of 2580 joules. You'll notice I'm using 3 significant figures because this is 4, this is 3, this is 3, 4, 3, 3. So we use the lowest value, which is 3 sig figs. Sig figs. All right. The change in enthalpy when the ammonium nitrate dissolves in water is 25.69 kilojoules per mole. Determine the mass of the ammonium nitrate in the cold pack using your answer obtained in section 6 of the and using section 6 of the data booklet. So what we have to do is first recognize that we're in joules. So our previous answer, 2580 joules, is equal to 2.58 kilojoules. So we absorb 2.58 kilojoules. Now it's telling us that normally 1 mole of it would make 25.69 kilojoules. So what we're going to do is we're going to take 2.58 kilojoules, divide it by 25.69 kilojoules mole inverse. You might be saying, Mr. Garcia, how do you know to divide? This seems wild. Well, that comes back to dimensional analysis. If I divide, my kilojoules will cancel, which we can do. Kilojoules cancels. And what I end up with is a 1 over mole inverse value. I will end up with a value that's 0.1001 over mole inverse. Now, when I have 1 over mole inverse, to clear this little negative sign right here, we actually bring it back to the top, and this becomes 0.100 moles, which is a great unit to have of ammonium nitrate. Because now I can take ammonium nitrate, 0.1 mole, 0.100 mole, and I can use the molar mass of ammonium nitrate that I figured out earlier. 1 mole is, or sorry, whoops. I'm going to drop my unit. 1 mole is 80.06. You'll remember that we found that before up here. So I'm going to use that value, and I will find that when my moles cancel, I will have 80.06, which we will round to, or sorry, not 80.06, my goodness, 8.06, which we will round to 8.1 grams. Anywhere within that range is totally fine and totally acceptable. Or I should keep the 3 sig figs. We'll go back to 8.06. Yeah, grams of ammonium nitrate, NH4NO3. All right. We find that this cold pack actually contains 9.5 grams. Whoops. Calculate the percent error. So percent error is how much we got off. Percent error is how far off we are, how far off we are. We can do this in two ways. We can take how much we should get, 9.50, subtract what we have, 8.06, and then divide it by what we should have. And that would get us a total. Sorry, we would also then multiply by 100 because it's a percent. And then that would get us some answer, which we'll get to in a minute. The other way we can do it is find our percent yield. With our percent yield, 8.06 divided by 9.50 times 100, then we get some value as well. And let's see what we can spot between these values. The correct answer is 15.7, and this value is 84.3. Well, 100 minus 84.3 gets you 15.7. So our percent yield and our percent error are just the opposite of each other. Anyways, that's our correct answer, 15.7%. Anywhere in that region is good. All right. Solid ammonium nitrate can decompose to gaseous nitrogen monoxide and liquid water. You'll notice they said the states. Therefore, you should include the states. NH4NO3, solid, decomposes into dinitrogen N2 monoxide O plus H2O, gas, liquid. To balance it, all we need to do is just drop a 2 in front of the H2O and we're good. All right, that's the end of the SL test. Moving on to HL. For HL, we need to really know our enthalpy of formation and enthalpy of combustion reactions. This is an enthalpy of formation. We note for a couple reasons. One, they said delta H standard F. Number two, we're going from something smaller to something bigger, which means we're forming. So because this is formation, our equation should be products minus reactants. So our products is negative 156 minus our reactants, which in this case is going to be negative 36.3 for hydrobromic acid plus a 0.1. So we get negative 156 minus a negative 36.2. When we add that together, we get negative 119.8, which is right here. All right. What is the enthalpy of reaction, enthalpy change of the reaction in kilojoules? Now, you'll notice this time they give you combustion. In combustion, it's the opposite. It's reactants minus products. So our reactants, which is graphite, negative 394, but you'll notice we have 2 of it, so we will multiply by 2. And we're going to subtract our products, which again, we have 2 of it, so 2 times CO2, which is negative 283. The negative will cancel with the negative, and we will just end up with our answer as D, 2 times negative 394 plus 2 times 283. Which equation shows the delta HF of ethanol? So formation, so we need to make sure that we have 1 mole. So it cannot be B and it cannot be D because those both create 2 moles. Now the question is, are we in our gas state or our liquid state? Well, ethanol is naturally a liquid. This is alcohol. Alcohol is a liquid. The natural state is liquid. We are forming a liquid. Moving on to number 4. What is the enthalpy change of the reaction? Once again, keep in mind that this is combustion. So we're going to have our reactants minus products. In our reactants minus products, we have C6H14. So with C6H14, we have a, where is it? Negative 4163 minus our products. Our products are the other ones, negative 1411 minus or plus a negative 2878. This negative will correct these into positives, and we have positive 1411 plus 2878 minus 4163. There's one answer that includes all these values with the correct signs, number 4 or number C, letter C. Number 5, what is the enthalpy change of combustion of urea NH2 to CO2 in kilojoules per mole? So there's a couple key aspects here. One, we have formation values. Formation values. Second, we are making a standard. Because we're making a standard, and you'll notice urea has 2, we need to divide everything by 2. That automatically nullifies A and C as options as they don't standardize it. The final thing that you may want to look at is that when we are looking at these values, the big difference here is um, whether our water value is positive or negative. You'll notice that here, 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 and here. So are we subtracting, or sorry, do we have a positive or a negative water value? Because this is formation, this is going to be products minus reactants. So when we look at water in this case, it should be 4 times our value of negative 286. You'll notice that in B, we do have 4 times negative 286, but in D, we have negative 4 times negative 286, meaning they carried a negative through. Because of that, we know our answer must be B without having to do any of the work. I did shortcut a little bit of this when I did this question on my own. I identified all the products and reactants and noticed that water was the one that was wrong. It takes a little bit longer, but not too much. Number 6, which of the following is a correct equation depicting the formation of butane from its constituent elements? All right. Well, first off, butane, if we count it out, has 1, 2, 3, 4 carbons, not 5 carbons. So it cannot be C. Again, this is a formation. It cannot be A. That's decomposition. So it's got to be B or D. The difference is when we use constituent elements, we still have to follow diatomic elements. They take precedent. So it cannot be D. Our answer must be B. 7, write the chemical equation depicting the enthalpy of formation of HCN. Well, the elements are H plus C plus N form to make HCN. Now, to balance it, I go like this. But the problem is when we're doing an enthalpy of formation, we need 1 mole. So I'm also going to add state symbols here. I'll do it in my final one. I'll divide everything by 1/2. So 1/2 H2 gas plus carbon solid plus 1/2 N2 gas reacts to form HCN. This can be a gas, liquid, solid, whatever. Um, so with that said, this is the rest of the tests. Please look it back if you need some help, and have a great night. And we are done.